every now and then I have to fill out paperwork, either at the DMV to get my driver's license or health insurance or some awful reason. I have to fill out paperwork and I have to enter it. It says, how tall are you? And I have to enter my height. And that is just a terribly vague and stupid question, how tall are you? What does it even mean, how tall are you? I mean, if you look at me and if they just measure how tall I am, well, it depends. Right now I have nothing on my feet except socks, so I'm not that tall. If I wear my normal shoes, I'm up here maybe, right? If I wear my high heels, right, I'm way up here. So how tall you are is sort of a vague thing. They're really asking how high are you, right? They have that thing with the stick that comes down and measures where your head is. It's not a measure of how tall you are, that's a measure of how high you are, right? So if they really want to know medically, really the actual question, if they want to know my anatomy, the question is how long are you? Right? What they should really do is get you up, on a table, and they should measure you like this. You lay here and measure the difference between the bottom of my feet and the top of my head. That'd be how long are you. That would actually be relevant. So whenever I'm at the doctor or something and they want to measure my height, I say, no, let's measure how long I am. And I kind of lay, and then it doesn't go well from there. But the point is, these kind of measurements are difficult when they have to do with a difference. There's absolute measurements, and there's measurements that are a difference. And this is what's tricky with potential. Sometimes we write delta V, sometimes we just write V. Okay? This wasn't a problem with force and field. Force and field are absolute. If there's zero force, nothing will accelerate. Everything's fine. If you apply a force, the particle will accelerate. There's a very clear difference. Zero is special. When there's zero force, things don't move. When you talk about energy, it always depends. The potential energy, well, what's giving you the potential energy, and where are you relative to it, and can you get closer, or what are we calling zero, and does it go to infinity? All these sorts of things. So that's why it's confusing, is that energy is always relative. However, we do like to write it without that delta on there sort of all the time. So what we have to do is come up with what we all agree is zero, okay? When I go to the doctor's office and they say, how tall are you, and they want to measure it, we all agree that 0 is the 4. And the shoes is just a little error, they don't worry about it, okay? But it's like everyone agrees 0 is the 4. Right now I'm 5'11" from the floor. I'm about 15 feet from the floor of the basement, but we all agree the 4 here is 0, so I'm 5'11". So let's see how we agree on this for electrostatics. So for a point charge, let's set U, the energy, potential energy, equal to 0, and therefore the potential equal to 0 at infinity, at R equals infinity. Now let's see then what this looks like mathematically. So we're going to have a charge, I'll draw it down here, plus Q, and we're looking on this axis. And to not think about difference, we're going to think about a point here, B, and then the point A we're going to put at infinity. Go all the way to infinity, and there's A, right there. Okay. So let's calculate that potential difference. So delta V, A to B, is a potential difference to go from A, where it's 0, all the way up to B. We just calculated what that is. That's KE Q times 1 over RB minus 1 over RA. Okay? And we know that's equal to the potential at B minus the potential at A. That's the definition of a difference. What we're trying to do is get a hold of this. Okay? So if we start plugging in things, we know that this special point A is infinity at the position R equals infinity. So this is 1 over infinity. So that's 0. That's 0 by math. Okay? That's not 0 because of what we said here. It's 0 because 1 over infinity is 0. So then we have KEQ times 1 over RB. That's what that side becomes. And now let's look over here. This equals VB minus VA. But this is 0. This is 0 by our definition. Define. So you don't want to mix those up. 1 is 0 mathematically. 1 is 0 because we said it's 0. Once you do that, you see the answer. The potential at any point B, really wherever you go, VB equals KE, and it's usually written like this, Q over RB. And usually we write it that way. It's not a potential difference. We all agree where the zero is. We don't have to think about difference anymore. Now you can kind of think of it as an absolute potential. In a world where it's 0 at infinity, you can have an absolute potential. It doesn't have to be a potential difference. As long as everybody agrees that that's the world you're in, as long as we all agree where the floor is, then it works. Okay? And it's a very simple expression to remember, KQ over R. And it's not just true here, since RA is all the way out at infinity, it's true at any radius. And if you're in spherical symmetry, it's not just true in this direction, it's true in all directions. So really for a point charge or a sphere of charge, this is the potential in all space around the charge, because you're always not quite at infinity. We can also use this to get an idea that a coulomb is a lot of charge. You may remember one of the very first lectures, I told you that a coulomb is a lot of charge. So let's apply this formula real quick numerically and see that that's true. Say I had my Van de Graaff generator here. And let's just say it were to make a coulomb of charge. All right. And then, you know, I like to play with this stuff. Let's say that I'm sitting here a meter away. All right, there we go. Let's say I'm sitting here a meter away, like that. What potential would I be at just a meter away? So the potential here would be K, 9 times 10 to the 9, oops, Q, 1 coulomb over 1 meter, be at 9 billion volts. Okay, we would definitely, you know, have some of this going on, or, you know, dead, right? 9 billion volts if you get a meter from a coulomb. In a real experiment, of course, the air would break down. Lots of things bad would happen before you got to 9 billion volts, and you couldn't really build up a coulomb. But the point is, a coulomb, huge amount of charge, creates huge fields and huge potentials. But we can now think, if we're careful, in terms of absolute potentials. We don't have to think always in terms of potential difference if we all agree where 0 is.